Hi, good morning and good afternoon. I am Mustafa Amir, Senior Petroleum Engineer and Energy Analyst. We will discuss how well integrity management can change from being seen as a production obstacle to a production booster. We will discuss how answering the right question transformed well integrity management from closing wells to real risk assessment. Our case is on failure in surface control subsurface safety valves. Do we really need to fix them all? What if we don't have the budget to fix? Should we shut them in to comply with well integrity barrier policy? Or shall we go and assess the risk and identify which failed subsurface safety valve should be fixed or not? As long as our discussion on surface control subsurface safety valve, then let's examine their advantages and disadvantages. First, their advantages include providing automatic mitigation and control for wells under production mode. They protect the wells in case of blowout, in case of the loss of the Christmas tree because of a collision, or they can close the well automatically in case of leaks in the wellhead of the Christmas tree or the flow line downstream the wellhead. Their disadvantages include impacting the well casing design to accommodate the surface control subsurface safety valve outside diameter. They cause labor exposure during operating the subsurface safety valve, during maintenance, during the wellhead integrity test. In addition, it increases the capabilities of regular activities. For example, if we want to conduct hydraulic frac operation on a well in the late field life, and we have surface control subsurface safety valve, we will be limited by the rating of the subsurface safety valve, or otherwise we need to go for workover to replace the completion with a frac string. It complicates the velocity string installation. For example, if we want to install velocity string while maintaining operable subsurface safety valve, it wouldn't be easy to set the packer under the subsurface safety valve. In addition, it's expensive to work over and replace because sometimes old wells, it could take few days to cut and pull the completion with the accompanying costs. Unfortunately, none of these wells went for recompletion, went for changing the subsurface safety valve with a new operable subsurface safety valve. Why? Because of the many reasons that we go through later. Wells with failed subsurface safety valve, they didn't go for fixing because wells were at their late life. The wells started with producing 20, 30 million standard cubic feet per day, and now these wells are producing 2, 3, 4 million standard cubic feet per day. So spending on recompleting these wells will not be as economically attractive, especially taking into account formation sensitivity and loss of 20 to 40% of gas production after completion because of formation damage. So as long as the situation is like this and we have failed subsurface safety valve, why not just keep these wells on production? The problem with keeping the wells on production is that the wells will be operating against the two barrier policy. Shell EOM's system, for example, highlights wells with failed surface control subsurface safety valve as a high risk and should be fixed within 2 months, or the organization should need to go through lengthy deviation. Deviation takes resources and management times to get done and is limited to 6 months only. After that time, the well gets highlighted again in the well integrity management system with red to top management. To operate the well after deviation expiry, that would be under the responsibility usually of the field manager and the operation manager. And in most cases, no one would like to take such a risk, especially if the mitigation actions accompanying running the wells usually include having a flare line and increased visual check on the well. Now we need to think of a different approach. We need to know if the wells are really safe to operate or not. We need to have the ability to assess if a well with failed surface control subsurface safety valve should be closed in until fixed, or it can be operated with a failed valve, considering some mitigations and some assessment points that the well should pass. To answer this question, we need to conduct a study that involves dispersion modeling of the worst case scenario that the well is producing against the atmospheric pressure because of the loss of the Christmas tree, for example. And that will give us, the dispersion model will give us the safe distance in terms of heat and in terms of H2S that for which people will be safe. We conducted the study on our field of interest that experienced the most failure in surface control subsurface safety valve, and it was at its late field life. First, we started with assessing the production potential of wells of interest. We didn't consider the daily production of wells. Instead, we assessed the blowout potential of wells, which is the production potential that the well can deliver at atmospheric pressure. We got that from matching the current well models and then model the wells on atmospheric pressure. Second, review all the production tests and assess the H2S concentration on all wells. Third, you measure what you get from the blowout potential survey you do and the H2S into a dispersion modeling. Performing the dispersion modeling exercise gives the safe distance around the well. So the distance, if people are farther away from the well with this distance, they are safe and they will not be impacted, even if the Christmas tree was lost and the well is under fire. People will be safe at this distance. And in our case, I really can't show the numbers we got from our study because it would need the approval still in progress. But in our case, we managed to get a blowout potential that covered 70% of wells in the field. The safe distance that we got from the dispersion modeling was then multiplied by a safety factor to consider as a safe distance, and the safe distance was then plotted on the field map around the major roads, the major facilities, the camp, and any well located in the area around facilities, around the camps, around the roads, was excluded for proximity to active location. So we choose wells that pass the location criteria should be away from facilities, should be away from camps, roads, or any place where people frequently visit by more than the safe distance. Finally, we check the mitigation action. That includes increasing wellhead integrity test frequency to make sure that the valves are operating, weekly measures of methane leaks and H2S at well location, constructing fence around the wells, confirmation with studies team that the well will not have any increase in production potential that could make it exceed the limit blowout potential. In addition, we confirmed that we have a contract in place with a company that can cap wells for well control purposes in case the top event happened. So wells on which we can apply the new policy, we can operate while having failed subsurface safety valves, should be under the blowout potential limit, should have H2S lower than the limit we define for the dispersion model. The location should be away from camps, main roads, facilities, by more than the safe distance that we get from the dispersion models. And the mitigation actions should be in place, including that the wells will not have any operation or any proposal from the studies team that increase its blowout potential below further than the limiting blowout potential. If wells satisfy all of these four categories, all of these four conditions, then the wells can operate with failed subsurface safety valve. But if the well doesn't meet any of these four checks, then the well should be operated with operable subsurface safety valve, or in case of having failed subsurface safety valve, the well should be closed.